So, welcome to this second paper of this session on mutation testing and debugging. We have a short prepping now coming next, okay?
Welcome everyone. My name is Mike Petka. I'm a PhD student from the University of Stuttgart, and I'm going to present you our work regarding extreme mutation testing in practice, an industrial case study. First, let me explain what extreme mutation testing is.
Okay.
Okay. So can the audience see my presentation now? Or shall I stop sharing and retry it?
Let me check. I will go to this.
Uh,
Yes. Okay. People are seeing you.
we were watching the video, and then suddenly the video stopped.
Yeah,
and we
because
see the beach.
I saw that there was a problem. Okay, and then I tried to change and I click on presentation instead of live backstage. Okay.
Okay.
So now it's fixed. Now you should be watching the presentation. Okay, and my camera below. Okay, so you can start, Mike. Thank you.
So I can start now, right? So it's not the video that is running. Okay. Okay, fine.
You're live.
Okay, I'm live. So again, so I first explain what extreme mutation testing is, right? So I was talking about this simple example consisting of 4 different classes and a simple test suite consisting of 3 different tests. And test 1, for example, may call method A, and test 2, for example, may call or test method B, but in this event also calls method E and F. And when we look now inside method F, we would see that this method is only partially covered. So we would write another test 3, which calls method F with different parameters and thus increase code coverage. And the concept of extreme mutation testing is now as follows. We pick a method that has either partial or full coverage, and then we delete any statements that are executed by this method. So we empty the method body completely. And that's, by the way, the reason why it's called extreme mutation testing. We do not mutate just a simple instruction, but the whole method. And then we rerun all tests that call this method. So in this example, this would be test 2 and test 3. And if both tests still pass, we consider method F to be pseudo-tested. It's called pseudo-tested because despite having coverage and calling these tests, the output of method F does not contribute to the test outcome, so whether it's successful or not to the test suite. So extreme mutation testing tries to solve some of the issues that the traditional approach has, namely the large amount of generated mutants. And because there are far less methods in the code than instructions, there are by default less mutants, and thus it's faster. On the other hand, it's of course a little bit more coarse-grained because you may miss some of the important mutants that may be relevant for the developers in the traditional approach if you are on an instruction level. And we found this technique very interesting and wanted to observe it in a realistic setting. And that's why we conducted a case study at Advantest. Advantest is a leading manufacturer for automatic test equipment to test semiconductor chips. So they provide hard and software to test semiconductor chips. And we were particularly interested in the part of the Java software. So we asked the following research questions. One, are the improved execution and analysis times of extreme mutation testing relevant in practice? Two, how do extreme mutation testing results impact the established practice of writing unit tests with code coverage? And three, which factors prevent extreme mutation testing from industry adoption? So our case study design looks as follows. So first we ran mutation testing. For that we used the tool PIT with the Descartes engine, which is very famous for Java applications. Then we used Jacoco to capture line coverage, and we used JUnit to run the unit tests. In the second step, we analyzed the reason why these methods were pseudo-tested. So we selected the methods, so a subset of these methods by name, size, coverage, and return type. And by size, we mean the number of lines of code that this method has. And in the last step, we interviewed 2 experienced developers and had an interactive session with them where we opened an IDE and demonstrated them how extreme mutation testing works and what their results are, and asked them several open and closed questions. And our results look now as follows. We had more than 11,000 unit tests, so quite a large test suite. And this test suite usually finished in 12 seconds. And it took with extreme mutation testing 13 minutes. Just for comparison, the traditional approach took about 37 minutes, so about 3 times as long. And the test suite called more than 2,000 methods, and it turned out that 291 of these methods were actually pseudo-tested, which is roughly 14%. So if you may ask if this is a large number or if it's not, you may look at the work of Niedermeyer, where they tested 19 open source projects, and the average percentage of pseudo-tested methods were 13.7%. So this is a perfectly average result. And we analyzed in more depth 25 of these 291 methods and found that the main reasons why they are pseudo-tested were either that there were no assertions in the code, in the test, sorry, they were incomplete, like it was obscured that some parts are not tested because it showed that it was covered in the coverage report, or these methods were called as a side effect. So for example, if you test a particular method that you want to test, but it also calls a logging method that you are not interested in, then this is a side effect of calling this method. And when we ask the developers which methods are for them relevant, and relevant means that they should be fixed, then they found that the methods with no assertions and the ones that were incomplete are worth fixing. And what was a little bit surprising is that they considered that this technique would be most useful when writing unit tests. So this is different than the traditional approach where you usually run mutation testing in a separate session. So these are our conclusions. Are the improved execution and analysis times of extreme mutation testing relevant in practice? And the answer is it depends. So I mean, we have this 16 minutes, no, was it 13 minutes, sorry, 13 minutes of extreme mutation testing and 37 minutes of the traditional approach. And if you run it in a build pipeline, it probably would hardly matter. When we want to run it by writing unit tests, we are comparing a couple of seconds to several minutes. So for that, it's still not fast enough. And analysis times are quite hard to compare because these have different precision levels. But of course, we can say that extreme mutation testing is a little bit or is easier to comprehend because we just have this method level. And on the second research question, how do extreme mutation testing results impact the established practice of writing unit tests with code coverage? We say that it's supplemental, so it makes code coverage, like in execution coverage or line coverage, a little bit more accurate. So in showing what is actually tested and not only executed. So if you would adjust all the lines that are considered to be pseudo-tested and remove them from the coverage report, we would have to adjust the line coverage from 89% to 82%. And we also want to point out that this effect would persist to some degree, because in another study from Vera Perez, it was shown that out of 101 pseudo-tested methods, less than 30% are actually worth fixing. So we want to actually include this adjustment of coverage in some form. And the last research question, so which factors prevent extreme mutation testing from industry adoption? We think that the main two reasons are tooling, because right now it's represented in a simple HTML report where all the pseudo-tested methods are listed. And we think that this would be better represented if we put this results in a code coverage report, like in an HTML report like Jacoco or in an IDE. And the second reason was development stage. So we think that it is more beneficial to use it while writing unit tests as a supplement to code coverage. But for that, it has to be much faster. Okay, thank you. So we have a little bit more time left for questions.
The load time. Okay. So, any questions from the audience? I have a question regarding the software project that you use it. Okay, from the semiconductor industry. Is that publicly available or something to reproduce the results? Or I
No,
guess
sorry,
not.
no. That's the problem with these industrial projects, right? So that you cannot easily share the software that they are using it.
There's a question in the chat. Xavier, congratulations you for the work, and ask you if you used Pete Descartes for the string mutation testing analysis, and if yes, if did you have a look at Descartes Reneri that generates a report with information on how to potentially fix pseudo-tested methods?
So the answer to that is yes. I used the Pete Descartes engine for PIT, but I haven't looked at the report with information on how to potentially fix the pseudo-tested methods. So, but that's a good point. So I will look into that.
Yeah, indeed. I foresee these tools more and more included into commercial offerings, let's say, okay, where you usually get for free, okay, reports on code coverage, okay, but I think this kind of these mutation testing tools, I think they should be started to be included there, continuous integration tools and the like. So any other question? Okay, so thank you very much, Mike, for your presentation. Okay, and remember that he will be transferred to a discussion room where you can join, okay, if you want to ask him some additional questions, okay? I'll leave you here, okay, to check for the last paper that will start in roughly a minute, okay? Thank you very much, Mike.
Thank you. Yeah.